Let's get started here. So test number 2 is on Monday. We will spend the last portion of class reviewing for it. We will complete factor analysis today. We will also discuss project number 2. And if there's still some time, we will start cluster analysis, our next section. Regarding class on October 30th, for those of you who do not know this, stat students should know this, but non-stat students may not know this, the Department of Statistics here is undergoing an academic program review. This is a common thing for departments to do, where they actually bring in external people from outside the university to review the department. It usually happens about every 7 years or so with departments. And the Department of Statistics academic program review is on Monday, Tuesday, and Wednesday. There is something on Wednesday at 9 a.m. that I'm kind of supposed to attend. Obviously, that's a problem then for our class. So if I have time, I will pre-record what we would normally go over next Wednesday. I will pre-record it so that you can view it versus actually coming here physically to class, although the room will be open. So if you really wanted to come here and watch the video, you can, but I recommend not. So if I have time, I will do that. For now, though, let's assume that we will be having a regular class here next Wednesday. If I do have the time and I do pre-record everything, I will post a message to the listserv to let you know. Okay, are there any questions about that or anything else before we get going here? Okay, so we're talking about factor analysis. And in particular, we're talking about common factor scores. Just to review what that is. Here's my factor analysis model, once again, written in terms of now matrices. So what we're looking for is what will be numerical values for this F vector for every single observation. So to some respect, it's a little bit like the principal component scores that we found earlier with principal component analysis. Now we're interested in factor scores. And there are two different methods that one could use to find these common factor scores. One is called, what did I use for the terminology? Bartlett. And one is called Thompson. And what these two methods do is basically take advantage of stuff that you would learn in Stat 870 and Stat 970 to find out what these common factor scores would actually be. Since they rely on coursework that is not a prerequisite for this course, you're not interested in understanding how the corresponding equations come about to find these common factor scores, but you are responsible for knowing how to apply the methods. So how to work with the matrices and also how to find these common factor scores using matrix algebra or using the fact_nl function in R. Okay, so let's talk about how we can do this in R. That's where we left off. So we're working with the goblet data once again, and we've, let's say, already rotated the factor loadings using the Varimax rotation method. And so what I'm going to do here is just simply estimate my factor analysis model once again, where here are my variables that I'm interested in. I'm going to have two common factors, goblet data set, rotation Varimax, and this is the new thing that we had not seen before with this particular function, the scores argument. Scores equal regression. If you remember, there's actually separate names, additional names for each of these methods. So Thompson's also sometimes known as the regression method, and Bartlett's method sometimes known as weighted least squares method. So that's where the regression method comes from for the score. And when you specify that and put all the results into mod.fit2reg, the scores are actually put into the scores component of the mod.fit2reg object. Just a quick note before we look at these scores. Note that we've actually used the fact-NL function essentially 3 times to estimate what would amount for the same model. In practice, you wouldn't do that. In practice, what you would do is just simply use this call to the function. I had three different calls because I was trying to illustrate what the function does. And so typically, you would only use this particular call. Okay, so for the first observation, common factor 1 has a score of negative 0.139, and common factor number 2 has a score of negative 0.895, simply. Now, to actually do the calculations using the matrix algebra formulas, what I've done is set up some code here for you can see how this is done with observation number 1. You are responsible for this, and I want you to take a look at it on your own, though, after class. To do the Bartlett or weighted least squares method, you say scores equal Bartlett. And here are the actual scores here. You will notice that the scores are quite similar to what we got with the Thompson or regression method. That should be expected. It's just 2 different perspectives of how to find the scores. You should not necessarily have large differences. Typically, they would be very similar. And I've never heard of anyone saying one is necessarily better than the other. Okay, so let's actually do a plot of the common factor scores. Let's take a look at the plot first before we take a look at the corresponding code. And you can think of this plot here as similar to what we would do with principal component scores. So what we see on the x-axis, we have common factor number 1, its corresponding scores. Common factor number 2 is on the y-axis. And what I've done is I've labeled each of the points with the corresponding observation number. And so what we see here, or what we're looking for, I should say, are possible trends, groupings, or maybe even outliers in this plot, just like what we did with principal component scores. So we can see, for example, that, we have 17, 4, and 5. They're kind of close to each other. Maybe that might be one grouping. Maybe 23 and 24. And depending upon how you want to take into account these common factor scores in the middle, you might have something that looks like this, or maybe you might even group those middle ones all together. Well, compare that to what we had with the principal component scores on page 45. And you will notice a lot of similarities. Again, and actually, I'll show you the common factor scores here. You can look at page 45 in your paper, if you have a paper copy. You can see how 4, 17, and 5 are together. 23 and 24 are kind of grouped together. And then we have kind of a middle grouping of stuff, similar to our middle grouping here. So we come up with these kind of an ad hoc way of grouping the observations that are very similar, the groups are, to what we have with principal component scores. Okay, so how did I do this plot? Basically what I did was I took the principal component score plot code and I just applied it here. And this in terms of a 2-dimensional plot. So I have a square plot. I find common limits for my x and y axes based upon the scores. Then I plot the score, so I simply take out the first score, put that on the x-axis, second score, y-axis. I put some horizontal and vertical lines at 0, and then I use the text function to allow me to actually plot then the observation numbers. So nothing really new there. Okay. And lastly, on page 46, then, I have a question. Suppose a different rotation method other than Varimax was used. Could these plots change? Could this plot of the common factor scores change? Yes or no? 50-50 chance of getting it right. Yes. Because then these common factors represent potentially different things. That's one of the issues that some people have then with factor analysis. Okay. So that then concludes test number 2 material. Any questions? Okay, so let's take a look at project number 2. That was posted to the course website since we last met. The project is the same format as last time. You can work in groups of up to 3. It is due Wednesday, November 6th at class time. It's helpful. It will be. I recommend that you take a look at problem number 1 before the exam. You do not need to complete it before the exam, but I think it would be helpful for you to take a look at it because it shows you, with respect to factor analysis, the topic of problem number 1, it shows you what I think is important for you to understand for factor analysis. Okay. So problem 1 is on factor analysis. Problem number 2 is on cluster analysis, our next topic. Let's just take a look at problem number 1 here. You're going to see a lot of similarities to the first project with respect to what we did with principal component analysis, because this data set, or I'm sorry, this problem uses the same data set as from problem number 1. So it's that job applicant data set, and you're going to perform factor analysis on it. So, get a red pen here. So first, part A, determine the number of common factors used. So, I guess kind of then as a review, kind of a test review, what will be, how could you determine how many common factors to use? You could do a PCA first, but I'm looking for, let's say, a final number of common factors. Sorry if that wasn't clear there. The final number of common factors. Likelihood ratio test, yes. What would be another way? Look at the residuals. So, I'm expecting you to look at both. Part B, using the Varimax method, state the estimated factor analysis model for the number of common factors chosen. So it's just a matter of writing out what the model is. Okay. Then part C, interpret the common factors. Make sure you interpret it in the context of the problem itself. So, what does a corresponding factor loading close to 0 mean for a common factor? What does it mean if it's positive or if it's negative? What will be common factor scores that would be, let's say, preferred by this company in terms of finding good applicants? In part D, examine plots of the common factor scores. Just use the regression method, just like what we did here. Interpret the plot in the context of the problem. In particular, look at job applicant number 42. Remember, this was something that we looked at in the last project as well. Now, you shouldn't only talk about number 42, but I want you at least, I want you to look at number 42 for sure. Okay, and part E should sound familiar. Suppose a late applicant submits his or her application after the factor analysis has been completed. The applicant receives 10s for all 15 original variables. So this is like the perfect applicant. Now, through using the previous model, find what the applicant's common factor scores are. Now, this is something that we haven't talked about directly about how to do. Now, if you remember with principal component analysis, what you would do is simply create a data frame with the 10s in there, and then use the predict function to find, well, what would be the principal component scores. The predict function doesn't work with this, with stuff from the results from fact-anal. So how would you find, then, the common factor scores? Use the matrix algebra formulas, exactly. So that's what you're going to need to do. Now note that when I was writing up the answer key, I had a little bit of a problem having R do the matrix algebra. For some reason, it wasn't interpreting a vector of numerical values correctly. And so what I had to do was I had to use a function called as.numeric in order to get R to recognize this vector as being a vector of numerical values. So when you do this problem, if you start having problems, think of what I just told you right there. And if you still have questions about that, please bring that up in class or post a question to the listener. Then lastly, part F. If the overall goal is to find the best individuals to hire, suggest who they would be with the help of the factor analysis model. Okay. And that simply is the first part of project number 2. Are there any questions? Okay. Moving along then. Let's move into the next section. This is not on test number 2. So this is cluster analysis. This is still in the overall, let's say, division of the course that I've created, where I would call this, let's say, exploratory data analysis. And this is the last section in this overall framework of how I organize the course. Now, think of cluster analysis in a similar mindset as what we were doing with, actually just with the common factor scores, and this is actually with the principal component scores for the goblet data, where we were kind of informally grouping the observations together. So we use principal component analysis, or we use factor analysis to help reduce the dimension of the data so that we could actually visualize our data in a smaller number of dimensions and then come up with some kind of groupings of the observations. In other words, similar observations are grouped together. Well, the grouping is often also referred to as clustering. So for example, this is a cluster of observations, this is a cluster, and this is a cluster. And what cluster analysis does in a multivariate data analysis class setting, it provides a more formal method to do this clustering, to find these groups. And you don't need to find the principal component scores first. You don't need to find the factor analysis scores, or common factor scores first either. Okay? So it's a formalization of this grouping mechanism. Why would someone want to do this? Well, you're trying to find like observations. Maybe, for example, you can think of it in terms of let's say, a marketing example where you have a big database of potential customers and you want to group similar customers together. This might then lead you to ways to market your product to those groups of individuals, or these clusters of individuals. And so that's some of the idea behind cluster analysis. One key aspect to understand with what we're going to be doing here is that we have no prior groups of the observations that are known before the cluster analysis. So like with the goblet data, we didn't necessarily have any idea of for each observation what a group would be. Was this maybe goblet, let's say, used for drinking liquid, or was this goblet used for storage of stuff? We didn't know that beforehand. Now, the reason why that's important is because in the next main section of our course, we are going to be talking about examples where we do know prior specific groups for our observations. We've seen one example of a data set like that already, that place-kicking data set that we talked about maybe about a month ago. If you remember, every single observation was either a success or a failure. Those are the two kinds of groups. Okay? In that particular case, what we're going to be interested in is trying to predict, given information on, we know what groups they come from, these observations, we're going to try to predict the groups. And that's essentially going to be the last portion of our course. We're going to make focus on that. But cluster analysis says, okay, we don't know what groups at all these particular observations come in. To help you out with some terminology that you might see outside of this class, non-statisticians often refer to cluster analysis as fitting into what's called an unsupervised learning technique. I guess unsupervised, the word came about because you don't know the original groups. Methods where you do know the groups themselves, like with the place-kicking data set, and when you try to predict the actual group, is often referred to by non-statisticians as supervised learning. I believe, I could be wrong, but I believe this terminology of supervised and unsupervised learning came about through computer science. Over the last 10 to 20 years, computer science has really gotten into how should I say? Well, examining, let's say, data sets, in particular, let's say big data sets, where you want to find groups of observations, and or you want to predict the particular groups of observations where the groups are known beforehand. And so they kind of have developed some of their own methods, and to some respect, things have merged together through both statistics and computer science. Okay. Also, I should also mention, just to give you another term, outside of this class, you will often hear the phrase machine learning. Essentially, supervised learning and unsupervised learning are types of machine learning. So, actually, you could say for the rest of this course, we're going to be doing machine learning topics. It's not a statistical term that is developed. I think it's more of a computer science term that has developed to refer to this. Okay, so there are a lot of cluster analysis methods. A lot. Partially it's because now people who do research in this are not necessarily only statisticians now. So there's a lot more people working in these areas. And there's so many cluster analysis methods out there. I wouldn't be surprised if you could teach a whole class on it. Well, we have, I think, 3 class periods set aside for this. So I'm not going to be able to tell you everything about cluster analysis. We will focus on particular topics in the area. Just to give you an idea of just how much information or how much has been done in cluster analysis and is actually ongoing, there's what's called a CRAN task view set up to show all the packages that are available in R that are with respect to cluster analysis. And you can see, as I just paged through here, there's a lot of packages. Whenever there's, let's say, a big topic area where people are using R to solve particular statistical problems, you will see what are called task views set up on the CRAN website, corresponding to all the particular packages that focus on that particular statistical method. And that's what this cluster analysis one is meant for. Now, also, then one of the recommended books for our course, the Everett and Hawthorne book, has a section on cluster analysis. But the author, the co-author, Everett, also has his own book on just cluster analysis itself. Again, to give you an idea of just how big this area is. You can actually obtain the book electronically from our library if you are interested in. Do note that you cannot download the whole book at one time. I think you can only maybe download 10 pages at a time. I have not bothered to do that. Sounds like a good thing for a graduate student to do. Anyway, so let's look at some more motivation behind cluster analysis and how it works. I have a very simple data set of 14 observations here. I call it my 2-variable data set. And So I've simply plotted x1 on the x-axis, so x2 on the y-axis. I've labeled corresponding observation numbers, or observations by their numbers. And so with this then, what cluster analysis does is tries to group like or similar observations together into one cluster. So for example, perhaps you might, I guess I'll just go to the next page. You might form this particular grouping. So there are 5 clusters here, 5 groups. And again, the way these clusters are formed is by finding similar observations, observations that are close to one another. Now also, you might think, well, how about we just form a group here instead, and a group here instead as well? Well, yeah, that's a possibility. Those observations are somewhat similar to one another. Maybe not as similar as to my original grouping, but they are similar to one another. And so a big topic that we will cover here is to decide, well, where do you stop this clustering? Where do you stop the grouping? Should I go with 5 clusters, or should I continue to group observations together until I have maybe just 2 clusters? And there are going to be particular methods available that will allow us to determine, should I have 2 or 5? Or might end up concluding 2 or 5 are possible. So you're going to see that there's going to be some leeway here. There could be more than one answer to a particular problem when I say go apply cluster analysis to a data set. Okay, that just takes us to page 5. So how do we determine then how similar or how close observations are so that we can decide should these observations be in a cluster together, or maybe they should be in different clusters? How do we decide on closeness of observations? Well, as you might see here, well, how about we just simply calculate the distance between the observations, maybe a Euclidean distance. All of you have seen before. Yeah, and then that's what we can do, and that's what we primarily will do. So here's the Euclidean distance, or you could say essentially, if you put a ruler down on a plot, if you only had 2 variables, let's measure the distance between the points. So the distance, d, between 2 observations, let's call them r and s, just to be general, is simply you take the xr vector of observations, subtract off the xs vector of observations, transpose it, and then do the same thing over here without the transpose. Take the square root. That is Euclidean distance that you've seen even before this class. So observations that are more similar to one another will have lower d sub rs values. Observations that are far apart, less similar to one another, will have larger d sub rs values. Now there is a particular problem with using Euclidean distance, and that is, suppose that you have observations that are measured in different units. Okay, we've seen this problem pop up in other places too already. So instead, what will typically be done, not always, but typically, is use standardized Euclidean distance. So in other words, in that d sub rs equation, just simply replace the x's with the z's. So you can see that, if I have a large data set, well, let me ask you this. Suppose I have a data set of size n. How many distances do you think I will need to find, do you think, in order to do a cluster analysis? N distances? And choose 2 distances. Okay? So let's say you have a large data set. You could have potentially a lot of distances. And so, because of that, there are a variety of different cluster analysis models where maybe you don't need to find all the distances. We will look first at methods that do find all the distances, and then we will look at methods that do not necessarily do that. If you do want to find all distances between two observations, there's a nice little function R called dist that you will see us use. Okay, so clustering methods. Now, as I said, you could probably teach a whole course on cluster analysis, so you might think there's a lot of methods here. Well, there are, let's say, 3 different groupings of methods that one could do for all of cluster analysis. Seems appropriate to do that. So please make that change. There's not 2, it's 3. The first method is what's called hierarchical cluster analysis. And the way that this works is simply you got some observed data points. You have some observations, and these observations are grouped in you could say a sequential manner. Meaning, let me start here. So if I just gave you this simple plot here, what do you think the 2 closest observations are? Come on, get out your rulers. Maybe 13 and 14. So the way that a hierarchical method works is that you might, let's say, group 13 and 14 together first. So if let's, perhaps I should have said this beforehand, maybe you could have started with, let's say, 14 separate clusters for the 14 observations. Now if I'm going to group 13 and 14 together, now I have 13 clusters for the 14 observations. Then next what you do, we're going to go in a sequential manner, find the next set of closest observations. What do you think? Maybe 1 and 2. So now I have 12 clusters for 14 observations. And perhaps then I say, well, maybe 11 is close to this cluster that's 13 and 14. So now I'm going to cluster together 11, 13, and 14. Oops. And so now I have a cluster up there. And you keep on going and going and going until eventually you get to a point where maybe you just have 1 cluster. And so you can see how we're forming these clusters in a sequential manner. That's hierarchical clustering. And in particular, what I had just described to you was a particular kind of hierarchical clustering called agglomerative. Agglomerative, that word, if you're not familiar with it, means to gather together. So agglomerative begins with each observation is a separate cluster. Clusters are successfully merged until 1 cluster is present. Now, if you have just 1 cluster at the end, that kind of defeats the purpose of cluster analysis. What you're trying to do is find distinct groupings. And so key then will be for us to determine where do I stop this clustering method. I don't want to go all the way to 1 cluster overall, and I don't want to have n clusters overall. I need to go somewhere in between. So again, agglomerative starts with assuming all your observations are individual clusters, and then in a sequential manner or successive manner, start grouping like observations together until you have 1 cluster. Now you could go the opposite direction and use what's called divisive. So instead, come back here to my plot. Start with everything as being 1 cluster. Now, obviously, you don't want that. So what you could do is maybe first split the cluster into 2 clusters. And then maybe split here. And so on. So you're being divisive in how you're forming the clusters. And you keep on going until every observation is a single cluster. Again, you don't want that to happen. So a key will be to determine, well, where do I go from 1 cluster to n clusters? Where should I stop? Okay, so that's divisive. It goes in the other direction, but still clusters are forming in a sequential manner. Due to time considerations, we will not do divisive. We will only do agglomerative. This is commonly done in a multivariate class. I rarely ever see a divisive ever talked about. But I at least wanted to let you know that it is possible, and there is a R function called Diana that allows you to do it. Okay. And then there's what's called non-hierarchical clustering methods. So this is the second of the three main groupings of cluster analysis methods. And the way that this particular method starts is maybe specify an initial number of clusters. Maybe let's say 5. Specify that you want 5 clusters. And then use a particular algorithm that allocates the observations to these 5 clusters in some kind of optimal manner. So that, for example, if I did specify 5 clusters, if we take a look at this particular plot here that we saw before, you would think that ideally I would want to have something like this. Well, a non-hierarchical method might originally, let's say, maybe say we're going to put this in a cluster, this is a cluster, this is a cluster, and then these as clusters to start there. And then it just successively, through an algorithm, which I will show you later, tries to find the best set of groupings so that you still have 5 clusters in the end. So essentially, what you're doing is you're partitioning your observations based upon a set of known quantity of partitions that you specify. That's non-hierarchical. And we will talk about non-hierarchical. The third method in cluster analysis is probably the newest of the three. It's called model-based, where you assume an underlying model structure to your data. So you say, my data came about through this model. You might think of it in terms of, let's say, a regression model. And you're saying that your data came about through some kind of a regression model setting. And based upon this model structure, you're able to then, let's say, come up with particular clusters of your observations. I will not discuss this particular approach. You are starting now to see this come out in multivariate books. In particular, Everett and Hawthorne dedicate one small section to it. Okay. So let's talk about agglomerative clustering. I can further subdivide agglomerative clustering into a whole bunch of other separate methods. It's interesting how a cluster analysis has a whole bunch of different groupings and methods and subgroupings and so on. Let's take a look at the first one here. We're going to talk about 5 different methods. The reason why we're talking about 5 is because no one method is the best overall. And we're going to talk about a method called nearest neighbor. You also will see this referred to as single linkage. Terminology, unfortunately, is not consistent across applications. And here's nearest neighbor. And in fact, I essentially already showed you what nearest neighbor was through when I was drawing on the plot. Start with n clusters overall, where each cluster is a particular observation. Merge the 2 clusters that are nearest to each other. Remember how I merged 13 and 14? Then define the distance between this new cluster and all other observations as the minimum distance between the 2 points in the cluster. What do I mean by that? I'll go back. So we said 13 and 14 are put together. So now I need to figure out what's the distance between this cluster that has 13 and 14 in it. What's the distance between that cluster and each of the other observations? And what the nearest neighbor method does is says, okay, 13 is closest to 11 in comparison to 14 to 11. So I'm going to find the distance between 11 and 13 is, the distance between 11 and the cluster that has 13 and 14. I'm going to find that distance is simply the Euclidean distance between 11 and 13 instead of 11 and 14. So then using that idea of how to find the distance between this cluster that's 13 and 14 in it with all the other observations, then I find the minimum distance between these clusters to decide, well, which observations would I join next. And because I've done this example myself, I know that what ends up happening is that 1 and 2 are joined together. Because that is a smaller distance than, let's say, 2 and 3, or 2 and 4, or even 11 and the cluster has 13 and 14 in it. So that's step 4. Step 5, continue this process of making clusters until you end up with one cluster in the end. So let's take a look at a plot. So I have even a simpler data set that has 4 observations in it. These are the 4 observations. And let's move ahead to the plot that's on page 11. So hopefully you can see where the 4 observations are. The big blue dots, and they're nicely numbered there. And what I've simply done is actually drawn in all the Euclidean distance. Again, typically you use standardized Euclidean distance, but since I'm just demonstrating what this method does, I decided just to simply use regular old Euclidean distance. So for example, the distance between observation 1 and 4 is 2.44. Okay, so let's walk through how one would actually do the nearest neighbor method. So which observation should be joined first into a cluster?
3 and 4.
3 and 4, because they have the smallest Euclidean distance. Okay. Now, in order to define the distance between, let's say, observation 1 and this cluster, I look at the minimum distance. So what would be the minimum distance? The 2.44. Okay. What's the distance between observation 2 and the cluster has 3 and 4? 2.83. So where I've drawn the lines under, those correspond to the distances I'm looking at. So based upon that, let's say step 2 of my nearest neighbor method, which observations should I join together? Or which clusters, I should say?
1, 3, 4.
Yeah. So 1, 3, 4. So I have a cluster with 1, 3, and 4 in it, and then I have a separate cluster with just 2 in it. So then, obviously, the next step would be then to join 2 with the remaining observations. But just to emphasize, well, what the nearest neighbor method does, what will be the distance between 2 and this cluster that has 1, 3, and 4 in it?
2.56.
The 2.56, because that's the minimum distance. Okay, that's simply how nearest neighbor works. So let's go back up to page 9 then. What I've done here is simply shown you, well, how do you find the actual Euclidean distance between observation 1 and 2? Make sure you understand how to do that in a matrix format. It's fairly simple. If I were to do this in R, I simply create a vector. How about I call it x1, and a vector call it x2. And then I take the square root of x1 minus x2, transpose it, times then x1 minus x2. The dist function allows me to find all pairwise distances between observations. It's fairly simple how it works. I create an object called set1. I'm going to put in my data, variable 1 and variable 2. And then just simply say distance, x equals set1, method equal Euclidean. And so now I have this, this set of distances. So the distance between observation 1 and 2 is 2.56. So why don't you see anything up here in that matrix? Because they're either 0 Or simply, for example, the distance between 2 and 3 is, oops, it's not listed there, is already listed here. So you have the symmetry. Now there will be times where you would like to have an entire matrix, let's say, of distances. And to do that, I can just simply say as.matrix with the results from the disk function. And now I have a 4x4 matrix, because I have 4 observations, that shows all distances. Notice on the diagonal of the matrix, I have zeros. Okay. So I think that will lead us to a good stopping point. Are there any questions? Okay, let's review for the exam then. Okay. So test number 2. Obviously, we'll start at 9 a.m. Again, remember, there is a class that is in here beforehand. So, it might take a little bit of time for them to get out of the classroom. But because of that, what I will do is allow you to have a little bit extra time. So maybe we'll go till 10:25 for the exam. Okay? There is a formula sheet. Hopefully you've already taken a look at it. That's on the graded materials webpage of the course website. You can look at that sheet on your computer during the exam. I will not give you a printed copy. The formula sheet actually contains all the formulas that we saw previously from test number 1, just in case you feel as though that will be helpful. I'm not going to test you directly on stuff from test number 1 material. But obviously the stuff that we did in test number 1 is kind of, to some respect, built upon then for the stuff for test number 2. So that's why I left it there. Also, of course, then all the corresponding R functions are listed on this formula sheet too. So with respect to the material that you're responsible for, if you remember the data distributions and correlations section, there was still a little bit of stuff at the very end of that section that didn't get on test number 1. That involved the eigenvalues, eigenvectors, and the multivariate normal distribution. You are responsible for that since you weren't tested on it before. Very small section. Then the graphics, principal component analysis, and then factor analysis. Nothing on cluster analysis for this particular exam. The test has 100 points on it. And this is the way it looks right now. I don't anticipate changes, but this is the way it looks. Problem number 1 is 16 points. I'm going to give you some data. You're going to need to use R to do some calculations. And perhaps do some interpretations, do some other stuff. And this deals with the graphics section, or graphics set of notes. Number 2, it's worth 37 points. Going to give you some data. You're going to have to use R with it, and it involves some stuff with principal components. Problem number 3, it's worth 21 points. Going to give you some data. You're going to do some R stuff with it, and it involves factor analysis. And number 4, I'm going to change things up a little bit, and we're going to have 26 points, And these are short answer questions. There are 3 of them. That they're not necessarily connected in any way. So similar to the short answer that you saw in the last test. And then lastly, number 5, there is going to be a 3-point extra credit problem. Okay, so that's the general layout for the exam. Again, just give you a little bit of a reminder about the test structure. I will pass out a paper copy of the exam, and this is what you need to put all your answers on. You essentially use the computer in front of you kind of as a calculator to produce numerical results that are needed or to produce graphs that are needed for the exam. Now, once you find, let's say, an answer in R, you need to write the answer down on your test. But you also need to show your work in some way. What this usually means is that you need to actually, let's say, put down a formula that was used to do a particular calculation. So, for example, suppose I ask you to tell me what the first principal component is with respect to a particular data set. Well, of course, you know to use print-comp to find the necessary coefficients, or are often called loadings, that are used in the principal component. But what you also need to do is tell me a little bit more about how you found that. So, for example, you could actually write out simply, start with this. Y1 is equal to x1 minus mu1 times a11 plus, and actually write out the particular components. So xp minus mu p a, I forget the exact notation I use, maybe AP1, or might be A1P. I don't remember off the top of my head which usually came first. And then, then you can say, okay, R found, this particular value for A, this particular value for A, and so on. Okay. You can say, well, I use print-comp to do the calculation, and here's a little bit of the information about the arguments. If you simply put a numerical result down without giving me any background about how you got it, I will not give you full credit. I was lenient last time because it was the first test, but I will not give you full credit. You need to show me your work in some manner. And this is for your own benefit because let's say if you did put down the wrong numerical result, well, how can I assign you partial credit then if you didn't show me how you came about it? So it's for your own benefit to put some information down about how you got the result. Let's see now. So again, the book is closed. The test is closed note and closed book. What you will have available to you are my R programs on my course website. So obviously, it's to your advantage too if you've looked at, downloaded the R programs before the exam, so you know where to find particular items that will be helpful for you for the exam. You are not allowed to access any of my notes. You're not allowed to access any answer keys to projects that are on my webpage. The only things that you can have open on your computer are R, TIN, RStudio, the PDF file for the formulas, and then a web browser pointed to my website, and then I guess also you can have a web browser open to the R help. Okay, so those are the only things that you can have open. Again, I can see what's on your computer screen up here. So please don't try to open up anything else. Okay, so that's the general structure of the exam and what's going to happen. Let's now review for the exam. So again, the data distributions and correlation sections where we're starting off. And we were talking about eigenvalues, eigenvectors, the multivariate normal distribution, how they're all kind of connected. Remember, the eigenvectors point in certain directions that kind of correspond to the ellipses that form the contours of the multivariate normal. Then the graphic section. The purpose of this is, or I should say, I guess just in general, how to implement all these particular plots. How to interpret, then, all these particular plots that we looked at. Those are important. Now, obviously, on an exam, I cannot say, I want you to turn in a parallel coordinate plot with the exam for 100 observations. Okay? I can't ask you to do that. But what I could do is say, I want you to construct a parallel coordinate plot and then interpret it. And put your interpretation on the exam. Or perhaps I might ask you to, let's say, maybe sketch a little bit on the exam what a particular plot looks like. Now again, if there's 100 observations in this parallel coordinate plot, that would be difficult, so you can imagine that I probably wouldn't ask you to do that. But I could ask you to sketch maybe a star that is in a star plot. So that it shows me that you understand how to construct the star plots, and you understand how they are actually constructed, because you can sketch one. A common theme then with the graphics section was to get as many variables on one plot as possible. Because this is a multivariate class, we have lots of variables potentially that we are interested in, and we want to be able to view all those variables, the corresponding data from those variables, graphically. And so we looked at a number of different ways then to do this. And we started off with simply a 2D scatter plot. But we can make the plotting points correspond to particular qualitative variables that might be of interest. So instead of just having, let's say, x1 versus an x2 plotted, maybe we could have x1 versus x2, and then have the plotting point correspond to x3, x4, and x5. Then we extended this idea to a 3D scatter plot as well, and also to a bubble plot. Then we looked at other ways to do plotting that kind of deviated from the normal scatter format that all of you would be familiar with before this class. And we looked at a star plot. Now remember how multiple variables are represented on the star plot. Essentially, each ray that extends out from the middle corresponds to a variable. Well, how far does it extend? Well, it corresponds to the size of that variable value for an observation. We also then talked about parallel coordinates plots. Again, how do we get lots of variables on the plot? Make sure you understand that. And also a trellis plot. Now this is where we use conditioning on variable values to help us look at multivariable data. I could ask you on an exam, describe for me how a star plot is constructed, but I don't want to see an actual star plot. So can you, in words, describe what a star plot is and how it's constructed? So that's the graphics section. Then we went to principal component analysis. Make sure you understand the purpose of it. Well, it's to be able to view multidimensional data, or to understand multidimensional data in a smaller number of dimensions. This is helpful when you have correlated variables. If you don't have correlation, then principal component analysis is not going to really help you. Then once we get these principal components, then we want to be able to interpret them. So make sure you understand how to interpret them. So overall, how does principal component analysis work? Meaning, how are the calculations done? What are we trying to do? Well, we're trying to maximize the variance of a linear combination of our x's. And then, the eigenvectors from either a correlation matrix or a covariance matrix play in a very important role. Then, how do we choose the number of principal components? Well, we looked at 3 different methods to do that. Then, how do we find the principal component scores? And what do we do with them? Well, we often plot them. Because now this gives us a graphical way of seeing what our data looks like in a smaller number of dimensions. And of course, make sure you're familiar with PrintComp. Remember, in particular, with the principal component scores, the predict function doesn't necessarily find it exactly the way that we want. So we had to make a little small change to the object that's created by PrintComp in order to get PrintComp to work. In order to get predict to work right. Make sure you understand why we needed to do that. And lastly, factor analysis. Obviously, what's its purpose? Again, you're looking for, let's say, the true dimension of your data. But the difference between factor analysis and principal component analysis in terms of a purpose is that you're hoping that you're going to be able to interpret then these new variables that we form, in this case, common factors, you're hoping to be able to interpret them better than what you did with the principal component analysis. And that was the whole idea behind the rotation of that. Now, there's a lot of terminology associated with factor analysis. Make sure you understand what a common factor is. A specific factor. A specific variance. What are factor loadings? What is a uniqueness? I could keep on going. There's a lot of terminology associated with this section. I guess also with principal component analysis, why do we typically use standardized data? Make sure you understand that. The factor analysis model, of course, a very simple question would be, state the model for me. Also, factor analysis equations. Essentially what these equations give us is what our correlation or covariance matrix look like in terms of our particular model. We use these factor analysis equations then with the multivariate normal distribution then, and then maximum likelihood estimation to find estimates for our parameters, the factor loadings and specific variances. A way that we assess then the fit of a factor analysis model is to look at residuals. Make sure you can find them. And I guess a question might be, well, find a particular residual. Am I asking you to do? Also, we have the likelihood ratio test that can be used to assess our particular model. Then a very important concept to understand with factor analysis is the non-uniqueness of common factors. And just for review, what does that mean? What do you mean by there's many different common factors? Yeah, this is where the rotation comes in. because the factor loadings is what leads you to an interpretation of what the common factors represent in terms of your original variables. Since these factor loadings can change due to a rotation, that can change then your common factors, your interpretation of the common factors, and thus that's what I mean by non-uniqueness of common factors. Then, of course, we have the common factor scores, which we talked about today. Make sure you know how to find them. Then doing plots of them. And what do these plots give us? And, of course, make sure you understand how to use the fact and now function involved. Okay. That's all I have to say specifically about the exam. We have about 10 minutes left here. Are there any questions?
Okay, I'll start.
Yeah.
One of the things with factor analysis is that sometimes things won't converge, right? So do you just abandon factor analysis at that point?
That is obviously a possibility. It depends upon what the convergence problem is. At the very simplest setting, that I guess you wouldn't even try to estimate the models. Let's say that you have too many common factors given then the number of original variables that you have. In that case, the simple solution uses a smaller number of common factors. Of course, then the question is, well, are those smaller number of common factors really representing your data? So, let's say, though, that you do choose a number of common factors that is reasonable and you don't get convergence. That means you can't use that particular model. What can you do? Maybe use a smaller number of common factors again, or if that's not satisfactory, you might not be able to use factor analysis.
So just keep dropping the number of common factors.
Again, this is an exploratory method. So, if I don't get convergence, if I don't get a model, I'm not going to be, let's say, as concerned as if I was, let's say, fitting a regression model to some data and I couldn't get that, depending upon what kind of model it was, I couldn't get that model to converge. If I have an exploratory method that doesn't work, well, I have other exploratory methods that will work, principal component analysis. Other questions? Of course, if you have questions between now and test time, please feel free to post a message to the listserv. I will be responding. But I just want to remind you that option is available. Well, I guess then we'll just end it with that. Like I said, after test number 1, I do think that this test is going to be more difficult than the previous tests. So please be aware of that. Please make sure you take the appropriate time to study for the exam. So that's it for today.